Chapter 7, we will discuss the transportation layer in the OSI model. Data networks and internet support the human network by supplying reliable communication between people. The transport layer of the OSI model is going to allow for efficient and reliable communication between devices. The data from each of the applications is packaged, transported, and delivered to appropriate applications on the destination devices. The process described in the OSI transportation layer is going to accept the data from the application layer and prepare it for addressing at the network layer. Because remember, at each section, the addressing changes to some extent. The transport layer prepares the data for this transmission across the network, and the source computer communicates with a receiving computer to decide how to break up the data into segments. It's also going to look at the media, how to make sure none of the segments get lost, also how to verify all the segments have arrived once it's been sent. When you're thinking about the transport layer, think of a shipping department preparing a single order of multiple packages for delivery, because your message or what you're sending to the destination may have to be broken into smaller packages depending on how that particular data is being sent. Our transport layer is responsible for establishing the temporary communication session between two applications, and then they deliver that. If you'll notice on the right, both in the TCP IP model and the OSI model, we have the transport layer, and this on the right is showing you the TCP IP model. At the transport layer, it moves data between the different applications. Those are the different software packages and types of things that you use to communicate, like your web browser, your email. How is it that you're getting the information there? How are you sending it? Then the transport layer moves the data between the applications on the devices in the network. The network layer provides a method of delivering the data across the network in a way that ensures the data can be properly put back together at the receiving end, as it's breaking it into packages. Inside the header information, it's going to have to give information so that it knows in what order things go in. You don't want to get your package out of order. It wouldn't make sense when it gets to the receiver. The primary responsibilities of the transport layer protocols are tracking the individual communications between the applications on the source and destination host, segmenting that data for manageability, and reassembling the segmented data into streams of application data at the destination. Also, in identifying the proper application for each communication stream. If you're sending an email, you're typically not going to want it to open up in a different type of application. With the transport layer, and it transports its data, at the transport layer, each particular set of data flowing between a source application and a destination application is known as the conversation. And you'll see this here in Figure 1. A host may have multiple applications that are commuting across the network simultaneously, but they may not all be sharing the same information. Each of these applications communicate with one or more applications on one or more remote hosts. And it's the responsibility of the transport layer to maintain and track these multiple conversations. You may have instant messaging going, as you may also have email. You may have your web browser open. If you have a voice over IP phone, you may have a phone call coming in. You may also be streaming video. The data must be prepared to be sent across the media in manageable pieces, and most networks have a limitation on the amount of data that can be included in that single packet. The transport layer will have services that segment the application data into blocks of data that are appropriate for size. And the service includes the encapsulation required of each piece of data. With your header, it's used for reassembling, is added to each block of data, and the header is used to track the data stream. And we can see that here in figure 2. You'll notice we have the different color-coded blocks. They're going to match up to your different color-coded arrows here. And you see they're not always together. So when it gets to its destination, all the green packets will line up together, all the purple, all the red. That's how it works. At the destination, the transport layer must be able to reconstruct the pieces and reconstruct them in order. You also need to be able to identify the application. There's many types of application or services running on each host in the network. And to pass data streams to the proper application, our transport layer must identify the target application that is being used. To accomplish this, the transport layer assigns each application an identifier, and the identifier is called a port number. So email, instant messaging, web pages, voice over IP, and video streaming will all have their own unique port number. And we'll get more into the port numbers in just a bit. We also have conversation multiplexing, and that is when we're sending some types of data, for example streaming video, across a network as one complete communication stream. And you could use all of the available bandwidth and prevent other communications from occurring at the same time. It also makes error recovery and retransmission of damaged data difficult because you're sending it as one large chunk. The figure to the right shows that segmenting the data into smaller chunks enables many different communications to happen at one time with many different users, and it's able to be interleaved or multiplexed on the same network. So we're able to use our network for more than one task. Without segmentation, only one application at a time could use the network, and this could be cumbersome. It would also slow down your productivity. To identify each segment of data, our transport layer adds to the segment, as I said before, a header containing binary data. And the header contains fields of bits. It's the value of these fields that enable different transport layer protocols to perform different functions in managing data communications. So we see here we have our network access, our internet, our transport, and our applications. In this diagram, it is showing you that with the TCP function of our transport layer, we have FTP, we have HTTP, which is your www, you have your SMTP, which is typically your email, and some DNS. Those are handled through TCP. Your UDP, or your user datagram packaging, is your DNS and your TFTP. All of those come down into our IP. The transport layer is also responsible for managing reliability requirements of a conversation, and different applications have different transport reliability requirements. IP is concerned only with the structure, addressing, and routing of a packet, and it does not specify how the delivery or transportation of the packet takes place. Now, with your transport protocols, specify how to transfer messages between our hosts. So TCP/IP provides two transport layer protocols, the TCP, which is the transmission control protocol, and the UDP, which is the user datagram protocol. IP uses these transport protocols to enable hosts to communicate and transfer their data. TCP is considered reliable. It is full-featured transport layer protocol, which ensures that all the data arrives at the destination. It checks to make sure it got there. If it didn't, it resends the information. However, UDP doesn't care. It doesn't check behind itself to make sure that the other end is there or that all the pieces were delivered successfully. As I've stated before, with TCP, it's considered a reliable transport protocol, which means that TCP includes processes to ensure the reliable delivery between applications through the use of acknowledged delivery. It kind of has a handshake. It makes sure it's there. With TCP, there's three basic operations of reliability, and those are tracking transmitted data segments, acknowledging received data, and retransmitting any unacknowledged data. TCP breaks up a message into small pieces, and those small pieces are broken up based on the media that it's being traveled across or the application it's headed to. When you click play here on this diagram, it is going to show you an animation of how the TCP segments being transmitted from a sender to a receiver, and I will let you do that on your own. These reliability processes place additional overhead on your network resources. The more overhead you have, the slower your network can become. While TCP is reliable, it provides more robust communication between applications. They also incur additional overhead, which I told you could slow down your network. There is a trade-off between the value of reliability and the burden it places on your network, and that's when you may want to use UDP. That provides just the basic functions for delivering data segments between the appropriate applications with very little overhead and data checking. UDP is known as a best effort delivery protocol. It makes its attempt and it hopes it all gets there. In the context of networking, best effort delivery is referred to as an unreliable because it doesn't check up behind itself, basically. UDP is similar to placing a regular, non-registered letter in the mail. The sender of the letter is not aware of whether or not the receiver is available to receive the letter, nor if the post office actually delivered it. TCP is kind of like the registered letter that you send out and you have to have a signature when the person receives it, and then you're notified that they signed for it. Both TCP and UDP are valid transport protocols, and depending on the application requirements, either one and sometimes both will work for the transport protocol portion. Application developers must choose which transport protocol type is appropriate based on the requirements of their application. As you'll see here, UDP can be used for IP telephone and streaming video. TCP would be your email and HTTP. You'll see here in the transport layer, the UDP required protocol properties are fast, there's low overhead, does not require acknowledgments, does not send lost data, and delivers data as it arrives. This is when you have your buffering going on with your streaming video, and if you miss some part of your telephone conversation, it's not going to send it to you. You just have to ask the person, what did you say? So that they know that you didn't get what it was they had just said. However, with our TCP, it's more reliable. There's acknowledgement of data. It will resend lost data, and it delivers data in order that it was sent. With TCP and UDP, to really understand the difference between the two, it's important to understand how each protocol implements specific reliability functions and how they track communications. With TCP, it was initially described in the RFC 793, and in addition to supporting the basic functions of data segmentation and reassembly, TCP is also shown in this figure to the right, and it provides connection-oriented conversations by establishing a session. It makes sure that the other end is there. It has reliable delivery, it's ordered data reconstruction, and there's a flow control established. When it establishes that session, TCP is a connection-oriented protocol. Like I said, it makes sure that it's there. It's very reliable with its delivery. It makes sure things are in order once it gets there, and it doesn't send it too fast or too slow based on the resources available. Once TCP establishes a session, it's then able to keep track of the conversations within that session based on the header information. Note, maintaining that a state information requires resources that are not necessary for stateless protocols such as UDP. So again, this is overhead. You do need to go through and make sure you understand the order of this TCP segment. You may see it again. Actually, I'm pretty sure you'll see it again. So make sure that you've gone through this, that you understand where the source port and destination ports are located, the sequence number, the acknowledgement number, the header length. This is a reserved section. You have your control bits, window, you've got a checksum, urgent, then there's the options, and then the application data size. So make sure you understand what those are for. With UDP, it's considered best effort. It's not necessarily considered reliable. UDP is a lightweight transport protocol that offers the same data segmentation and reassembly as TCP, but without TCP reliability and flow control. UDP is such a simple protocol that it's usually described in terms of what it does not do compared to TCP. Connectionless, UDP does not establish a connection. It's unreliable delivery, it's no order data reconstruction, and there's no flow control. Although UDP does not include the reliability and flow control mechanisms of TCP, UDP's low overhead data delivery makes it an ideal transport protocol for applications that can tolerate some data loss. And you'll see here that the UDP datagram header is much smaller. These datagrams are sent as best effort by the transport layer, and a few applications that use UDP are the DNS, which is your domain name system, video streaming, and voice over IP. One of the most important requirements for delivering live video and voice over the network is that data continues to flow quickly. When you have a large overhead, you may have more buffering, and it may take longer for your videos to resolve. The transport layer must be able to separate and manage multiple communications with different transport requirement needs. Consider a user connected to a network on an end device. The user is simultaneously receiving and sending emails and instant messages, so it needs to know how to get the information back and forth. How's it going to separate those multiple connections? Well, email may be going through port 110. Your web pages go to port 80. Sometimes you may see it going out of port 8080. And then here it has internet chat going out of 531. So they're not all trying to travel the same direction. In the header of each segment or datagram, there's a source and destination port. The source port number is the number for this communication associated with the originating application on the local host. So you have your application port. Here we have 110. That was email. The message is delivered using TCP or UDP. And the protocols and services requested are identified by the port number. You will get into the different port numbers. You should be able to learn these quite easily, and the ones that we're going to go over, you're going to need to make sure you understand and know. Like I said, port 80 refers to HTTP or your web services. When a client specifies port 80 in the destination port, the server that receives the message knows that web services are being requested. With FTP, you're going to have ports 20 and 21. And the source port number is randomly generated by the sending device to identify a conversation between two devices. This allows multiple conversations to occur simultaneously. In other words, a device can send multiple HTTP service requests to a web server at the same time, and the separate conversations are tracked based on the source ports. The source and destination ports are placed within the segment, and the segments are then encapsulated within the IP packet. The IP packet contains the IP address of the source and the destination. Remember, the IP address needs to be known so it knows where to deliver it. The combination of the source and destination IP addresses and the source and destination port numbers is known as a socket. And this socket is used to identify the server and services being requested by the client. It is the combination of the transport layer port number and the network layer IP address of the host that uniquely identifies a particular application process running on an individual host device. And this combination is called a socket, and the socket pair consisting of the source and destination IP address and port numbers is also unique and identifies the specific conversation between the two hosts. That way they don't get confused. If you've ever wondered, how can I send this to that location and it keep up with all those packets? It's because of this socket information. With the creation of sockets, the communication endpoints are known so that data can move from the application of one host to the application of another host. And the source port of the client request is randomly generated, and the port number acts like a return address for the requesting application. That way it knows that it got there. The Internet Assigned Numbered Authority, the IANA, assigned port numbers, and there are well-known port numbers. Those are 0 through 1023. We have registered ports. Those are 1024 through 49151. And then we have private or dynamic ports. The registered TCP ports are the ones listed here in purple. The well-known TCP ports, you need to make sure that you know. Like I said, 21 is FTP. Also 20 is FTP because you have a sender. You have 23, which is Telnet. 25 is SMTP. 80 is HTTP. 143 is MAP. 194 is Internal Relay Chat. That's IRC. And then you have your secure HTTP, which is HTTPS, and that is port 443. Some of the well-known UDP ports, 69 is TFTP and 520 is RIP. RIP will make more sense to you as we go along. And then our well-known TCP UDP common ports, 53 is DNS, 161 is SNMP, and 531 is AOL Instant Messenger and IRC. Sometimes it's necessary to know which active TCP connections are open. As you'll see here on the right, at the command line on your computer, you can type in Netstat, and you can see here we have TCP. This one tells you that it's been established with Cisco. And we have our local address, and we know here that they have been established. Here, this one's at 192.168.0.2. That's a NetBIOS. Then we have 3 HTTPs. Here's another HTTP, and then there's Cisco's. Let's go back one. This information that is printed out here for your Netstat, that will help you also when you're starting to do some of the Wireshark activities for this week. None of your labs for Chapter 7 will be done in NetLabs because it's going to require you or ask you to use Wireshark and use certain websites. And as I've stated before, within NetLabs, we cannot give you access, or we do not give you access to the internet. So in order to get the correct information for these assignments, you're going to need to run Wireshark from your personal computer, and it is a free service if you haven't already downloaded it. Sometimes it is necessary to know which active TCP connections that are open and running on your network host, and the Netstat can let you know that. If you have unexplained TCP connections, those can pose a major security threat because they can indicate that something or someone is connected to your local host and something's going on in the background. In a previous chapter, we explained how protocol data, or the PDUs, are built by passing data from an application down through the various layers to create the PDU. That is then transmitted on the medium, and at the destination host, this process is reversed until the data can be passed up to the application. Well, some of the applications transmit large amounts of data, and in some cases many gigabytes. You just think about how large a bit of information you may be sending. Now that information needs to be broken down into smaller portions or data packages in order for it to go across the network. TCP and UDP handle the segmentation a little bit differently. In the figure to the right, it shows how each TCP segment header contains a sequence number that allows the transport layer functions of the destination host to reassemble that piece of information. It just puts it back in order. However, when you send it through using UDP, it just tracks the conversation between the applications, and they're not really concerned about putting the information back in order. Here's this activity that you can work on to make sure that you understand what it is that you're working with. You try to decide, let's say, who connectionless is, who does a session establishment, who has flow control. You'll just grab these, pull them over, and then check to see if you have them correct. And you can go through this. These are great learning resources that are available to you.